we have the Computer and Thought Award. And this year's Computer and Thought Award is presented to Guy van den Broek. And he has done tremendous work in statistical and relational artificial intelligence and the study of tractability in learning and reasoning. So just to cite the award, the Computer and Thought Award is IJCAI-'s Early Career Award, premier AI award for researchers under the age of 35. Congratulations, Guy. Okay, please.
Thanks so much. It's really special for me to be here. I was at my first IJCAI in 2011 in Barcelona, and since then it's been my favorite conference. And over there I was listening to Malte Helmert, Vincent Konitzer, Stuart Russell introducing Daphne Koller, and I was thinking, wow, if these Computer and Thought Award winners would even look in my direction, I would be so honored. So it's really very strange for me to now stand here. And making these slides, I was thinking, what would myself from 2011 like to hear from the Computers and Thought Award winner? And I think what I would like to hear is, please help me make sense of this research field. So I would like to spend maybe 10 minutes trying to give some perspective on what's going on. And then the rest of the talk, I'll try to explain what I did and why I care about the problems I work on. And I'll specifically talk about high-level probabilistic reasoning and trying to find some new synthesis of learning and reasoning. And then at the very end, so I'll try to keep it together, but then at the very end I have some personal messages for a bunch of people that I would like to do. Okay, so how do we make sense of this research field? So I was recently reading a book, and I think it does a good job of explaining the current state of AI. It talks about deep learning. It says that that deep learning approaches the problem of designing intelligent machines by postulating a large number of very simple information processing elements. They're arranged in a network, and then there are certain processes for facilitating or inhibiting their activity. Think about stochastic gradient descent and so on. And on the other side of the spectrum, a very different approach is knowledge representation and reasoning, which takes a much more macroscopic approach. There, the belief is that intelligent performance by a machine is so difficult that it doesn't make sense to start from scratch. It doesn't make sense to do everything end to end. And so you try to build a system that has the complexity to do very advanced information processing and basically deal with anything we can give to the computer that we can communicate to the computer. Now, so the book I was reading was actually Computers and Thought by Ed Feigenbaum and Julian Feldman, and this book was written in 1963. Just to tell you that really there's nothing new under the sun. And this dilemma that we have in our AI community has been there for at least 56 years. Of course, this is the book that this award was named after, and it was in some way the earliest book about AI, trying to collect all of these initial papers of the field. Okay, so let's look maybe what this dilemma really is. So on the one side, we have pure logic, if I can kind of abstract away some details. And so pure logic is really good at slow thinking, being deliberative, cognitive, model-based, and try to extrapolate from what we know to come to new conclusions. However, already 8 years ago when I was a junior PhD student, people will often tell me, oh, pure logic is brittle. And it would always make me very sad because I'm so fond of logical approaches to AI. And of course, logic is brittle because noise, uncertainty, incomplete knowledge are all things that we struggle with when we do things logically. And so on the other hand, we have pure learning, and this is maybe for, you can think about deep learning. This is fast thinking, it's instinctive, it's perceptive, it's model-free, and it allows you to interpolate between everything we've seen. And it has some amazing achievements, just like logical AI has a bunch of very impressive achievements. And now I'm going to say something that is maybe controversial for some and not for others. I think at some point we thought that there was this dilemma, but in the last few years, what has become really apparent is that pure learning, very much in the same way that logic is brittle, pure learning is also brittle. A lot of these issues that in the past few years have come about, of bias, fairness, explainability, attacks, issues with calibration, unknown unknowns, trying to verify behavior to be correct, robust and safe, deal with changes in the environment, changes in the distribution. All of these issues are really issues where if you just do pure learning and you kind of give up on the idea of knowing how the world works, then you really fail to incorporate a sensible model of the world. And okay, so no one is booing. So it's maybe controversial, but I think this is a fair statement given the recent developments in the field. And so what is really going on is now we're doing a lot of learning, but we still have this knowledge that we need to incorporate in order to address all of these issues. And in the past few years, I've been trying to collect ways in which people now deal with knowledge and what traditionally would have been dealt with using logical approaches and knowledge representation. And I think these days, if you're really honest with yourself, a lot of the knowledge that we have about the world is baked into our Python scripts, the ways that we decode and encode cleverly our vectors, the ways that we fix incorrect outputs to make sense. And a lot of the applications of AI are really machine learning plus a whole bunch of rule-based decision systems that try to glue everything together. A lot of knowledge is also put into the way that we design data sets, and some of the authors that I've contacted asking them, how did you add this world knowledge to your machine learning model? They gave me permission to say that it's all just a big hack. And that's a little bit sad, because in some sense we went backwards. We can do these amazing things that we couldn't do before, but the way that we deal with knowledge in the world is less principled, scientific, and it's not as intellectually satisfying as what we had earlier. So all hope is lost? Well, not really. Actually, already for several decades, there is something. There is something in between, which I'm going to call probabilistic models of the world. And the goal there is to do AI by building joint distributions, by building a model of the world that incorporates a whole bunch of knowledge and that allows you to do a whole bunch of reasoning, while at the same time also being statistical and allowing for important parts of this knowledge base to be learned from data. And of course, there's a whole lot of different types of models. Causal models, I think now everyone agrees, are super important. Relational models, probabilistic programs. And I'm going to somewhat abstract from the choice of model and what it can express. So really, this dilemma that has existed for 56 years is really a false AI dilemma. You don't have to choose between these two things. And even today, you will hear people say that it's really one or the other, and that's just, I think, wrong. So why isn't everything solved then? If we can just build probabilistic models of the world, we can do learning and reasoning, what is there left to do? So for the rest of the talk, I would like to highlight some of the contributions of my work, and along these two questions. When we went from pure logic to building probabilistic models of the world, what did we gain and what did we lose? And then at the same time, when we went from probabilistic models of the world to just doing end-to-end black box learning, what did we gain and what did we lose along the way? Okay, so first question. We start from pure logic and we turn now our approach into building probabilistic models of the world. What did we gain? Well, it's clear we gained the opportunity to deal with uncertainty, to deal with data in easier ways. But what did we lose? Well, we lost the ability to do high-level probabilistic reasoning. And let me make that clear by a famous example now in my field, which is this cards example. So here the idea is that you would like to build some agent that reasons about a deck of cards. And so you have 54 cards, and the question is, what is the probability that the first card is hearts? And it's pretty easy for you to come up with the answer. It's 1/4. So let's try to see how we do this automated with an AI system. So the standard approach, you open your AI textbook, would be to build a probabilistic graphical model, let's say a factor graph, and this factor graph will have 52 random variables, which are the different positions in the deck of cards. And so all of these cards could be any of the different types of cards. So now we have our representation of our knowledge, our model of the world, and now we ask questions of it. We would like to ask what's the probability that the top card is hearts. We take our standard algorithm, and that's it, right? Now, if you would try to do this, what you'll usually see is that this probabilistic graphical model that you've built is fully connected. Because all of these cards have to be different from each other. There is some kind of global property, some high-level knowledge that you use, and if you encode it in our representations, this is what you get. And then because the algorithms that we build in our community, they all exploit the sparsity of our graphical model, any of the algorithms you'll find in your textbooks will end up building some table in memory with 52 to the 52 rows and run out of memory. So that's a little bit crazy, right? So what is going on here? So for us, this is a super easy question. It's a high-level reasoning question. And for us, this is easy, but for our algorithms, this is really hard. And it turns out that the properties that we use to reason about these types of problems, you can call them first-order reasoning if you like first-order logic. You could call it symmetry if you like group theory, or you could call it exchangeability if you like statistics. And so these are really the properties that we have, that we know that certain objects are indistinguishable. And so a lot of my work is on the topic of lifted inference, where we try to build algorithms that exploit these types of properties in order to do high-level reasoning, just like we could in first-order logic back in the good old days of logical AI. Okay, so what should we do if we want to solve this problem? Well, we have to model this distribution at the first-order level, and I'm not going to talk about all of the different languages that are out there to do this. I think Pedro may mention Markov logic networks very soon. There's probabilistic programming languages, and so on. But even in first-order logic, you can write down this distribution, and it looks like this. For every position in the deck of cards, there is a card. Every card has some position in the deck, and in every position in the deck, there cannot be two cards that are different from each other. If there are two cards, they have to be the same card. That's it. And so now the goal of lifted inference is to do reasoning at a high level. And theoretically, that means that we would like to compute certain things, answer certain questions, efficiently in the size of the domain. So it doesn't really matter how many cards there are, we would like to scale with the number of cards. So how does this relate to learning, right? So this was just logic so far. Well, in most of the standard machine learning, what we do is we make the IID assumption. And this means that we have a bunch of data points here called X and Y. They could be people. And we have a bunch of features for these data points, whether they're smokers, what job they hold, and so on and so on. And now when we make the IID assumption, we assume that these people have nothing to do with each other, and we have no way of relating them. Now, in the field of relational learning, we try to get rid of this IID assumption. And there you have suddenly a bunch of relations available to you to express how these people are connected. For example, you can say that smokers are more likely to be friends with other smokers, colleagues of the same age are more likely to be friends, people are either family or friends but never both, and so on. Universities in California are more likely to be rivals. Now, what is the issue? If you do this, and you build your probabilistic graphical model, you again get this very densely connected thing that is completely infeasible to deal with. And so a lot of my work is on how to plug in high-level reasoning here in order to still be efficient and do what we could do with just logic. And I'm just going to give one technical example of roughly like the gist of how this works. So here you have one piece of knowledge. It says that if you're a smoker and you're friends with someone else, then that someone else has to also be a smoker. Very simple piece of world knowledge. And now what we would like to do as our task is to count how many possible worlds there are. This is in some sense the easiest possible task you could try to solve. And if you would do this with a graphical model, you would again run into these issues. However, it's quite easy to see that you can compute this count efficiently. And I'll quickly show you. So let's say that I give you already a database of everyone that smokes and everyone that doesn't smoke. All right, so this is some piece of extra information that I gave you. So now you just have to do the case analysis. For example, if you're a smoker and you would like to be friends with some other smoker, this is allowed. This is totally okay. It's not required, but it's allowed. If you're a non-smoker, you can also be friends with another non-smoker. That's totally fine. If you're a smoker and you would like to be friends with a non-smoker, this is forbidden by this logical rule that is our knowledge about the world, and the other direction is allowed. So now what we have in the end is that everything is allowed, every friendship is allowed, except for the k friendships times n minus k friendships between the smokers and the non-smokers. What if we know that there are k smokers, but we don't know exactly who smokes and who doesn't smoke? Well, then we just count how many possible databases there are of k people that smoke out of a group of n people. And then finally, we don't really know how many people smoke. This was not part of the knowledge we had about the world, but we know that it's some number between 0 and everyone. And so now what we get here is an equation that is efficient to compute, and it answers our question. And it does so by doing high-level reasoning about this exchangeability and symmetry between all of these people. And so this is roughly how lifted inference algorithms work. And so the main contribution at the theoretical level of my work in this area is a particular proof and theorem, which says that FO2 is liftable. So what does this mean? It means that if you would like to do these types of counting problems where we would like to compute how many worlds there are, and every possible relation that is used always involves two people, and every kind of dependency between the properties of all of the people always involves just two people. This is FO2. Then it doesn't really matter how many people there are, how many cards there are in your deck of cards, how many entities there are. You can always do this efficiently. And so a corollary of this theorem in logic is that if you have a statistical model of the world and you would like to reason about it, at least for these types of questions, then, for example, what's called a partition function, then again we can do everything efficiently in Markov logic, relational factor graphs, and all of these representations. So all of these questions I showed you earlier, including the question about the deck of cards, all of these are provably efficient, even though if you wouldn't use high-level reasoning, you would get completely stuck. So can everything be lifted? Sadly, the answer is no. So this is another insight from a few years ago that as soon as there's a third person involved, things get more complicated, and also in logic. So if you try to say that there's some dependency between three people in the world, then it is possible for there to exist some model of the world where you can no longer efficiently reason, assuming some complexity assumptions. You may also wonder, what about learning? So this was all about reasoning. I would like to ask questions of the world. What if I just want to learn a model of the world from data? And so here there's also a lot of work on what's called lifted learning, where the observation is that high-level reasoning, which is again afforded by this connection to first-order logic, allows you to learn better models, but also learn them faster. And some interesting insight from that work is that this tractability, the ability to do high-level reasoning efficiently, that it seems to be a great inductive bias, and it allows you to also generalize better. So that's some kind of fundamental insight into the learning process as well. Okay, so this was very briefly how high-level reasoning about first-order logic ends up transferring to probabilistic models of the world, and how we're trying to bridge this gap between the two. And really what this is it's a confluence of ideas. My colleague and friend George Verghese has this beautiful kind of philosophy about how in research confluence of ideas and the meeting place of streams of thought leads to these amazing breakthroughs. And there's a bunch more of these confluences of ideas that I don't have time to talk about, unfortunately. And so one of them is probabilistic logic programming, where we try to combine logic programs with probabilistic AI and also build these algorithms and systems and languages. A second type of confluence is between databases, database theory and database query evaluation, meeting probabilistic AI. And so here I would like to refer you to this book that I recently wrote with Dan Suchu on query processing on probabilistic data, if you would like to know more. And then finally, what's also very exciting is the confluence of formal methods, where SAT modulo theories is a very important technology, but a purely logical one, together with probabilistic AI, and try to do probabilistic reasoning and probabilistic ways of doing formal methods and verification. And this is sometimes called weighted model integration. And so if any of these things sound interesting to you, I encourage you to maybe go to my website or Google and find out about these exciting other meeting places of streams of thought. Okay, so this was all I could tell you about how we bridge the gap between pure logic and probabilistic world models. For the rest of the talk, I would like to briefly go into how do we connect probabilistic world models with pure learning, what is most popular today in the field. And we'll try to find a new synthesis of learning and reasoning along the way. And so the first observation here is that there is another perhaps false dilemma here. And it's a dilemma between these classical AI methods, these models of the world, let's say Bayesian networks, decision trees, that have clear modeling assumptions. We understand them well. But on the other hand, there's neural networks which have amazing performance. They're black box, and we kind of struggle to understand exactly what they're doing, but they just perform so much better that it's not even a competition. Okay? If what you want is to optimize the loss function. So is this really a false dilemma? And that's a question that I don't have a final answer for, but what we're trying to investigate is the following. We're trying to build new representations and new machine learning paradigms that allow you to do much more of the things we could do with good old-fashioned AI and world models, while also getting the great performance we expect from our machine learning today. And we're kind of inspired by this field of tractable probabilistic models, and I'm going to just refer to them as probabilistic circuits. And these are similar to deep architectures in that they're kind of a layered architecture, but they're inspired by logical models. So this is just a logical hardware circuit. And the only thing we did here was sprinkle some probabilities over the edges of this circuit. And what these things do is they represent a probability distribution. You plug in some world, and you end up evaluating your circuit in a feed-forward manner. You take a bunch of weighted sums and products, and what you get at your output is the probability of that world. And if you're interested in this general area, I would like to refer you to this tutorial we presented at the UAI conference 3 weeks ago on tractable probabilistic models. And you may also know them as some product networks, arithmetic circuits, PSDs, gut-set networks. There's a large family of related representations here. So why do we care about these representations? Well, they have properties, and they have really amazing, beautiful properties. Properties you wouldn't expect from a machine learning model per se. You could read conditional independencies from the structure. You can interpret the parameters, try to do explainable AI. You can learn parameters in closed form. You don't always have to do non-convex optimization. If you have a bunch of questions you'd like to answer, they could even be linear in the size of this representation, like computing conditional probabilities, doing map inference, and even much harder tasks like taking expectations, computing KL divergences, entropies, logical queries, all sorts of decision-making queries. All of these have been shown to be efficient on some type of probabilistic circuit. So this is great. Here we have a representation that is somehow more powerful, more close to knowledge representation and reasoning types of representations. So the real question is, how much did we lose? Because obviously we gained a lot. And so here again, I would like to refer to the tutorial for the details and all the citations of all of the great work of other people that went into this table. But the summary is that when you would like to do density estimation and you would like to learn distributions of the world and compare tractable probabilistic circuits with intractable models, things like essentially deep generative models like MAID and VAEs, then it's quite competitive. There's several data sets where the tractable models even get higher quality models than the intractable ones, even though they support all of these goodies I showed you on the previous slide. And so this is very encouraging because this kind of tells us that you can maybe have both. You can have strong representations with beautiful properties, and you can also perform well in today's machine learning environment. But what if I only want to classify, right? So far I was just talking about building distributions of the world. What if I just want to classify an image as being, let's say, a digit? Well, let's say we just want a conditional probability distribution. So recently here we introduced this representation called logistic circuits, which is in some sense a discriminatively trained probabilistic circuit. And I'm not going to explain exactly how they work. It's very similar to the slide I showed you earlier, where you just multiply and sum a bunch of probabilities in a feed-forward manner. But the nice thing is now that you can start to use them just as black box function approximators. And they're not really scalable enough to solve ImageNet, but maybe we can try to at least bridge the gap a little bit. And so remember that the observation was that decision trees, Bayesian networks, if you would like to use them for something as simple as even MNIST or fashion image classification, their error rates would be 3, 4, 5 times larger than that of a simple neural network. So let's first aim to bridge that gap. And so if you train a logistic circuit in the particular way that we did, which is, again, something we're working on and maybe we don't fully understand yet, then it turns out you get very competitive performance compared to classical AI techniques, random forests, SVMs. And it even outperforms something like a convolutional neural network with 3 convolutional layers. And if you would really like to get better performance on these simple image classification tasks, what you need is already a ResNet, which is a quite advanced architecture. But what's really interesting here is that in order to learn these representations that have all of these nice properties, you actually don't need as large of a model as you would need to learn a very effective deep neural network. So in order to beat these logistic circuits, you already need to train a ResNet that has an order of magnitude more parameters. And again, we're still trying to understand exactly the properties of these learners and representations, but one thing that's already very clear is that if you have smaller data, then learning simpler models and tractable models and models with nice properties and that give you a nice inductive bias ends up being way more data efficient. So we're very hopeful that this entire field of probabilistic circuits, tractable models, and logistic circuits will actually be a useful synthesis of logic reasoning and also learning. Okay, so again, this is finding this nice thing at the intersection of probability, logic, and deep learning. So now I would like to, for the last minute or two, go back to this earlier observation that if you just do pure learning, then in some sense, what you do is something that is as brittle as just pure logic, because of all of these issues that arise when you don't properly take into account a sensible model of the world. And so our hope is that by building these new representations, these world models, we can also combine them with some learned classifier, some machine learning model, and try to do some reasoning jointly about how a classifier behaves in a particular model of the world. And so this is the work that my lab is currently doing and focusing on, and I would just like to give you a few kind of insights that we recently had. And so again, here we have a learned model, f of x. This could be whatever you want. I mean, sometimes it depends, but this is just something you learned to optimize accuracy. And then separately, you have a probabilistic model of the world, maybe a probabilistic circuit, a Markov logic network. And we would like to solve these hard problems by reasoning about these two together. And so here's an example of something that we recently did. We would like to know what we can expect of classifiers that have been learned when we apply them in the world that is represented by a probability distribution P of x. And so here's the equation. It basically says, if I observe a few things called y, then what do I expect the output of my classifier to be if I'm allowed to look at this distribution, P of x, in order to figure out what is actually the likely state of the world. If I can do probabilistic reasoning about P of x to figure out what f of x is going to do. And of course, the application here is to do predictions when you have missing features at prediction time. And so what we see here is that if you find the right combination of representations of f of x and p of x, you can efficiently compute these things. And this should be very surprising because this looks like a very, very intractable problem. If you do this, then it's quite easy to start outperforming standard techniques people use in this space, like imputation and some more advanced techniques for dealing with missing data. And the takeaway message here should be that nice properties of representations allow you to do this reasoning that maybe we didn't think was possible before. Another example of something we've worked on in this space is trying to jointly reason about some classifier, let's say logistic regression, and some distribution of the world. And what we're trying to do here is trying to explain what this classifier is doing using the distribution of the world, which it has been trained on, as a means to kind of reason about its behavior. And specifically, we're asking, if the world looks like this distribution, then what part of our data is enough information for us to conclude the prediction of f of x? And then here you see an example of how we use this. Here we have 2 digits from MNIST, and I grayed out a bunch of pixels. I don't tell you what their color is, but I tell you that the white pixels are pen strokes. And you can argue about it, but to me, the top one, kind of the white pixels look like a 5, and the black pixels look like the negative of a 5. And then the bottom white pixels, to me, kind of look like a 3. And so what we've done here is we've come up with these pixels, and we know that in the distribution P of x, if I observe all of these pixels, I will for sure guarantee that the classifier is going to make the prediction that it makes. Now, which prediction did this classifier actually make? Well, the top one was indeed a 5, but the bottom one was not a 3, it was a 5. But reasoning about the distribution of pixels, we have now learned that just looking at the pixels on the left allowed the classifier to conclude that this was a 3, because in the distribution, this is what you expect to see. Okay. Conclusions. I tried to frame my work in these 2 dimensions of, if you start from pure logic and everything we can do there, all of the amazing achievements of that field, and we would like to go to probabilistic models of the world, what did we lose and gain? And I think there the takeaway message is that bringing high-level representations and general knowledge, at the same time also allowing us to do efficient high-level reasoning about the world is a problem that is important in logic and in KR. And we've made progress bringing it to probabilistic world models, but of course, there's still work to do there. And then on the other side, I would like to argue for bringing back some models of the world in order to deal with all of the problems of machine learning of today, to deal with missing data, shift in data distribution, bias, fairness, explainability. Because once we bring back models of the world, we can support all of these new tasks, some of them I showed you, and we can reason about what we have learned. We can learn something and then actually ask questions of the thing that we have learned. And of course, it's important to do all of this without compromising the performance of our learner, and we cannot just go back to learning bad functions. Another conclusion is that I would like to emphasize there's a lot of value in working on pure logic and pure learning, and I really respect people that work on these two fields. But I also think that for the long run, we can do more if we find a good synthesis, some confluence of probability, logic, reasoning, and learning. And then for my final conclusion, I would like to really, in 56 years, that whoever wins the Computers and Thought Award then will think of this dilemma between these 2 approaches to AI as being something ridiculous, a false dilemma that obviously is not true. So I hope we can work together to get rid of this complete misconception. Okay, all that's left is now for me to thank a few people, and I'll try not to get too emotional. I'm of course very, very grateful for this enormous honor. I'm grateful to IJCAI, the organizers of this conference, the organizers of the association and the awards committee. I would like to especially thank my PhD advisor, Luc, and people that know his work also know that a lot of his ideas shine through in what I try to do. I would like to thank Stuart, Dan, Christian, David, George, Rina, Lisa, Dan, and a bunch of people that I probably forgot because they've been so supportive of me, and it's been really wonderful to have them. I would also like to thank a few people that kind of work on the background, people that are postdocs or senior students, but that have very, very significantly impacted the way that I think. And so those people, I think, are Kurt Rieses, Wannes Meert, and Arthur Choi. So I'm very grateful to them. And then I just had such generous collaborators. I've always enjoyed tremendously working with Matthias Niepert, Jesse Davis, Sigrid Nijs. I learned so much from them. And really, there's too many people. I cannot list all of them. But I'm very grateful. And I'm also very grateful to my wife and my family for all the support they've been giving me. And then finally, I'm so lucky to have this amazing group of students at UCLA in the Starry Eye Lab, and my postdoc as well. They're super talented, and they'll go on to do great things, and I feel so lucky to have them. And then I would also really like to emphasize that everything I presented here, if you disagreed with it, forget it, but if you agreed with it, then don't give me credit. These are the ideas that come from the statistical relational learning community, statistical relational AI community, the probabilistic programming and logic programming community, the community on tractable probabilistic models, knowledge compilation. So I also hope that they will see this award as a validation that what they do is important. And I would also then finally like to thank my sponsors. Thank you all for your attention. One question?
Thank you for a great talk, Guy. I have one question, and this is about the notion of tractability. I mean, we are used to defining tractability by things like tree width, horn clauses, some structure. I think that the tractability notion here is that the circuit can fit in memory. Namely, your representation is simply can fit within memory. That's the notion of tractability, and the inference is linear on whatever you have. If that is correct, how do you extract, how do you know how to get this tractable model?
So that's a great question, thanks. So I think there's kind of two notions of tractability. So one is, what can we learn that we know is tractable, as you say, some representation in which we can do linear time inference. And the other one is, how do we write down our knowledge in such a way that we know that we can reduce it to maybe one of these tractable representations, compile it, do reasoning on it. And so there, tree width is of course a very important classical notion. However, tree width of course doesn't cut it when you want to do high-level reasoning, because everything I showed you has high tree width. And so there we're trying to, and then so this FO2 idea is definitely one way of quantifying what is tractable. But there's more work that needs to be done on essentially measuring when do you have enough symmetries, when do you have enough structure to be efficient. And I don't think I have the final answer there, but yeah, so tractability is not just one thing, for sure. Thank you.
Thank you.
Great. Thank you.